Hey, in the last class, we learned how to differentiate polynomials, and we want to continue learning new rules of derivatives so that we can differentiate different types of functions without having to go through all of the algebraic gymnastics that went along with limits. Right now, I want to look at differentiating the function f of x equals e to the x. Now, we cannot use the power rule here because the power rule is meant to work when the base is x and the exponent is a number, but here the base is a number, specifically e, and the exponent is our variable. So this is different and we cannot use the power rule here. What I want to do is I want to use the limit definition because we're going to end up getting something interesting. And once we've done this once, we won't have to use the limit definition again when we're dealing with e to the x. We can just use the derivative that we end up calculating. So let's use the limit definition here. If we want the derivative of this, we've got the limit as h approaches 0 of our function at x plus h minus f of x all over h. And then we can use our function here, e to the x. If we have f of x plus h, this is going to be e to the x plus h, and then minus e to the x all over h. Now, we can look at e to the x plus h, and we can actually write that as a product. That's going to be e to the x times e to the h. Remember, when we have a sum of exponents, we can split it up into a product of two exponential expressions. And then if we look at what we have here, there's something we can factor out. Both of those terms in the numerator have an e to the x. So we can factor out that e to the x. So we're going to have e to the x. I'm actually going to bring it out front. E to the x times, and we've got e to the h minus 1, because e to the x is the same as e to the x times 1. So we've got e to the h minus 1 all over h. And then if we look at this, we are looking at the limit as h approaches 0. So the variable in this limit, the thing that we're looking at changing in this limit is h. If we look out front at e to the x doesn't have an h in it. So with respect to the variable h, this is effectively a constant, and we can bring it outside the limit. So we've got e to the x times the limit as h approaches 0 of e to the h minus 1 over h. And then if we look at this limit, there's no x in it. So assuming this limit exists, this is going to be a constant. This is going to be a number like 2 or 7 or 4.6 or pi. We don't know what this limit is yet, but it's going to be a number times e to the x. So assuming this limit exists and this function is differentiable, the derivative of e to the x is some number times e to the x. We just need to figure out what that number is. Now, we don't have any algebraic tricks that we can use for this particular limit because e to the h does make things a little bit more complicated. What we're going to do is we're going to just make a table of values, picking some small numbers near 0 for h and evaluating it. Now, I know you don't want to sit here and watch me do a whole bunch of calculations when we're really just going to use a calculator. So I'm just going to give you the table of values. Bing bong! Here is a table of values for the right-handed limit as h approaches 0 from the right. I will let you do your own for the left-handed limit if that's something you would like to go through. But if we look as h approaches 0 from the right, as we get smaller and smaller h values, the function values are getting closer and closer and closer to 1. We could look at the left-handed limit as well. We would see the same thing. And so this limit here is equal to 1. And so we have e to the x times 1, which is just e to the x. So let's think back to what we were doing in the first place. We were differentiating the function e to the x, and for an answer we got e to the x, and this is actually quite curious because we haven't really seen this happen for the most part with other functions. Generally, when we differentiate a function, we don't get the same answer out, but this does happen with e to the x. So I'm going to write out as a rule, the derivative of e to the x is just e to the x. And now that we have calculated this once, we do not have to go through the limit definition again. We can just use this as a fact. And we can use this to differentiate other similar functions. Let's do one quick example. Let's find the derivative of 5 e to the x. So this isn't just helpful for differentiating e to the x by itself. We can differentiate other functions that involve e to the x using some of the other rules that we've seen. We know that if we want to take the derivative of a constant times a function, we can just pull that constant multiplier out. So this is the same as 5 times whatever the derivative of e to the x is. But we know that the derivative of e to the x is just e to the x. We just saw that here, and so our answer is 5e to the x. In fact, any time we have a constant times e to the x, when we're differentiating, the constant can go out front, and when we differentiate e to the x, we still have e to the x with that constant multiplier out front, and we end up with the same thing that we started with. So the derivative of any function that is a constant times e to the x is going to end up being itself as an answer.